Yes, I'm here. I'm in Zoom. Just in case, Zoom people can if
So I will let Yogi take the floor. Apologies. I'm trying to get the... Yes. So, Yogi, can you make some noise?
Yes, I can make some noise.
Okay, good. So you can start hosting. There you go.
Okay. Yeah. So hello everybody. Good evening. And today we have a astronomy on tap, Copenhagen, and we have it dedicated to the Earth this time. The Earth and how special it is. So today is April 13th. Yesterday was April 12th, and it was the day when Soviet Union sent first man into space. Sorry, I'm from Russia. I'm biased. I need to mention that. And second thing is that 22nd is the day of Earth, and that's why we chose today's topic as it is today. And we're going to have two lectures today, and the first one is going to be by Dr. Lu Pan from the Copenhagen University, and she's working on Mars, and today she's going to talk about Earth, Mars, planets of the solar system. And then we're going to have Dr. Hannah Diamond-Lowe, who's going to talk more about exoplanets because she studies exoplanet atmospheres, and we're gonna see what makes Earth special, I guess. And in the between, we're gonna have a short quiz between two talks, so stay on. And yep, I guess now we can start with Dr. Lu Pan talking on seismology in the solar system.
Okay, shall I share my screen now? Yeah. Can you see my screen right now? No?
Sure.
I can't hear anything, but okay, great. Thank you. Yeah, so today I'm going to talk about solar system seismology and how we can understand the interior the interior of solar system planets by listening to the heartbeat of the planets. And I mean, to start with, I don't know if you guys ever think about what is inside the planets. Apparently, in the 17th century, scholars have already thought about this problem. And this is one of the sketch from that time. And people had this idea that Earth was hollow and contained many fiery hotspots in the center. And they are connected by these canals. And finally, they led to the eruption of volcanoes on the surface. So this German scholar, he had wrote this book about subterranean world. And that has, he had this idea about the subterranean world consists of this interaction between fire and water, and that can explain the volcanic activity and tide on the surface. So he was partially right about the volcanic activity. We actually can have a lot of evidence by looking at what is happening on the surface. We see active volcanic eruptions that indicate there is something hot. These hot magmas come from the subsurface world. We also detect a global magnetic field around Earth. And this is related to the outer core of the Earth, which is made of liquid iron nickel alloy. We also observe a lot of earthquakes that are telling us that our Earth is actually an active planet. So all of these surface activities are actually driven by the hidden forces inside our planet. And so you may still ask why we care about this. As I said, that the planet's interior are the heat engine for all of the surface activities. So right now I'm giving you the answer before we start talking about how we get there. But you can see these are simple models of how we see, like right now, what we understand about the interior of planets. And for Earth, we have this solid inner core and liquid outer core made of iron nickel alloy. And the convecting liquid outer core is the main reason that we have this strong magnetic field globally. And that could have protected us from these high energy particles from the sun. We have a silicate mantle and a very thin crust. So compared with Earth, we don't really know a lot about other planets. We think they also have this core, mantle, and crust structure, but we actually don't have a lot of data except for the measurements of moment of inertia. And but we can already see some differences between these different terrestrial planets. For example, we know that Earth is geologically active today, but Moon and Mercury, because they're much smaller, smaller planets, they cool down much faster, and they are right now geologically dead, or there are only very weak activities happening on the surface. We know Mars is kind of in between these planets. So Mars we observe a lot of volcanic activity, but much less than the Earth. So we can kind of see something is determining what is happening on these different planets. And another reason that we care about the interior planets is that rocky planets interior, they tell us how they form. So from what we understand about planetary formation right now, that planets are made out of this gas and dust left over from the protoplanetary disk. And this dust aggregates and they form large balls of dust that are really hot because of these energy from gravitational energy as well as the radioactive decay of these elements. And the planets cool from the outside, but the interior of the planets are still very hot. So when they are formed, these materials start to differentiate. And by differentiate, I mean that things like to be together. For example, iron, nickel, these metals, they come together and they sink to the bottom to form the core. And you leave the silicate mantle and the lighter elements, they go up in the crust. And this is similar to ice cream. For example, if you have a box of ice cream and you leave it out for a long time or in the fridge or out of fridge, like if you just leave it there for a long time, the ice and cream would segregate through time. And this is because the ice doesn't like to be with the cream. So when you heat it up, they will separate. And this is similar to what is happening inside the planets. So by looking back at the interior structure of different terrestrial planets, you can kind of come back to how these planets were formed, like what happened when they're still baby planets. So so now that I hope I have convinced you that planetary interior is interesting. So the question is, how can we get to interior planets? So I don't know about you guys, but I have growing up, I read a lot of science fictions about going to the center of the Earth. The story by Jules Verne, where they traveled into this volcano and into different worlds, wonderful worlds in the center of the Earth. And I also recommend a Chinese science fiction writer called Liu Cixin. He wrote a lot of science fictions, but this one is a very short story about the astronaut traveling to the center of the Earth, and she cannot come back. So she asked someone from the surface of Earth to take something like an AR glass to show her around on the surface. It's a very touching story. So there are a lot of ideas about how we can travel to the center of the Earth, but have we got there? The answer is we have only reached a very short distance. So the deepest borehole is this Kola super deep borehole. This is on the boundary between Russia and Norway, I believe. And this is drilled by the Soviet Union, and the drilling actually terminated in 1992 because the temperature was too hot. And it has reached a depth of 12 kilometers. So 12 kilometers to the radius of Earth is actually a football to a football field. So we are really not there yet. And 12 kilometers is not even penetrating through the continental crust, which has an average thickness about 30 to 80 kilometers. And it tells us it's very difficult to drill a hole into the center of the Earth, and we haven't really tried again in 30 years. So if anybody wants to try, like, take it. We don't really have other ways to travel into the center of the Earth. So we have to think about other techniques to infer what is going on inside the planets. So the question is, if we can't get there, how can we know about the center of the planet? So I put here some food, and I like food as analogies. And these have a common point that you need to know whether they are good or not before you open it and eat it. So for example, for the egg, if you want to know how whether it is raw or cooked inside, one of the easy way to do it is to spin the egg. If you spin the egg, it will, if it's fully cooked, it is solid inside, the spin will be very stable. While if it is liquid inside, you'll see it wobble around a little bit. For the steak, I'm not a master chef. I know people can do it, can know whether steak is well cooked by touching it. But for me, I take the temperature, and if it is 57 degrees C, it is medium rare, and it is a very good indicator of what's inside the steak. And for watermelon, I grew up, my parents always take me to the farmer market to buy watermelons. And the way that they always do it is to knock on the watermelon to listen to the sound of it. And I learned recently there is even an Android app that helps you to listen to the sound of the watermelon and decide whether it is mature and sweet or not. So just remember those points, and we'll come back to it later. So today I'm going to mostly talk about InSight mission. InSight mission is a mission to Mars. The full name is Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport mission. So this is, I think this is a very special mission. You may have heard about Curiosity rover, Perseverance rover, and other types of missions to Mars. But this is actually the first mission that really wanted to address the question about the interior of Mars. So it was launched in 2018 on May 5th, and it's about half a year to get there. It landed on November the 26th of 2018. So it has been a couple of years operating on Mars already, and it is still operating and listening for more quakes on Mars. The InSight mission has 3 ways to probe the interior of Mars, if you still remember about the egg and steak and watermelon. So first, it's going to observe the rotation. It has an instrument called RISE. And this is a radio science instrument that's going to observe the rotation of Mars. We have a heat growth sensor called HP cubed. It's supposed to dig into the subsurface of Mars and take the temperature. And then there's the seismometer called SEIS, and it's going to listen to the sound on Mars and to figure out how seismic waves travel through the Mars interior. It also, so on the rover, it also has a robotic arm, which is very important for the mission because we need to deploy this instrument on the ground. And that is one of the main objectives is to combine, put this on the ground so that they can measure the interior of Mars. We have the solar panel, and we also have some weather station that's going to listen to the temperature and pressure variations around the lander. So I'm going to talk about these 3 main instruments. The first instrument is the radial instrument, which tracks the rotation of the planet. As I said, like the egg, it will wobble a little bit if there is liquid interior. Just like I said in the beginning, for Earth, we had the liquid outer core, and that's one of the reasons we generated this global magnetic field. And on Mars, we think there might be a liquid outer core as well, but it might be smaller so that we didn't, so that it's not convecting. We didn't observe this, we don't observe this global magnetic field, but still we want to know whether there is a liquid outer core or not. And this radio instrument will help us understand that question. We then have the heat flow probe. We also call it the MO. This is the name for the heat flow probe is HP cubed, short for heat flow and physical properties package. It is actually a self-probing thermometer. And I'm putting here a little animation made by the DLR to show how this MO actually works. So it has this spring inside, and to use the recoil of the spring, recoil force to push itself down this it's more like a push hammer than a drill. The plan for this heat probe sensor is to drill into 5 meters into the subsurface and measure the temperature change. It would be the deepest hole we drill if it is successful, but we had a lot of difficulties with this instrument. So with the first try, we have penetrated into the subsurface about 30 to 35 centimeters. The whole mole, the entire length is about 40 centimeters. So it's not there yet, and then it was stuck. It didn't move for some reason. So we were trying to figure out why. At first, people think it might have hit a rock in the subsurface that we didn't know before. And then we tried to look at what is happening. We moved away the support system to look at the mole itself. We see that it has like if you keep pushing, it doesn't move a little bit, and sometimes it bounces back. And in the lab at JPL, the engineers have started to do a lot of simulations for the same instrument, and they have realized it is very likely because the soil is not cohesive enough to support the mole, so it doesn't go deeper. So the JPL engineers have come up with a method to help it dig. They decided that we can use this arm to push the soil next to it, so that it has more compaction from the soil. And this helped a little bit. It went a little bit deeper, but then it also bounces back a little bit. So these kind of activities were happening on and off for almost 2 years. At the end, we were able to, with the help of the arm, the mole completely went into the ground. And on the right, you can see the animation of the mole in the ground with a tether connected to it, but it doesn't move around. So this is when it is still digging, but you can see that the tether doesn't move inside. Because the whole mole is underground, there's really nothing more we can do with the arm. And this is why after 2 years of great efforts by the engineers, we have decided that we're letting it go and not continuing the efforts to dig into the subsurface of Mars. So this is a sketch from the team, and this is what we think has happened. There is a layer of drill request, and beneath that there's an unsolidated layer of soil, and they have very low cohesion, and it doesn't really help the mole to dig deeper. So after 9,000 hammer strokes, we have compacted the area around the mole, but we don't have any compaction along the surface that can help it go deeper. So that is where our adventure with the mole stops. It is unfortunate, but it is part of the challenges of going to a different planet. And we learned something about the Martian soil that we really didn't think about before. So then I'm going to talk about the seismometer. The seismometer has a name called SEIS. It's short for seismic experiment for an interior structure. A seismometer is basically a device that is sensitive to vibrations. So it listens to the sound, listens to the movement of the planets. It works like a pendulum. So here I'm showing the simple form of a seismometer, and on the right, this is the image of the actual VBB seismometer that we have put on Mars. And it works as a pendulum on the framework, and that is put on the surface of Mars. And we put the lower image shows a wind and thermal shield that we cover this seismometer to protect it from the wind and the thermal variations from the environment. The seismometer has to be very sensitive, but also extremely robust. to survive the landing and the launch of the vehicle. This is not the first time that we have tried to put a seismometer on Mars. With the Viking 2 lander, this is in the 70s, we have already tried to put a seismometer on Mars. So this box is the seismometer we have put on the Viking lander. But little did we know at that time, Mars has a lot of wind, a lot of weather, a lot of noise. So that because of that, coupling with the lander, we hear a lot of noise from the lander itself. And this is why it is crucial this time that we want to put a seismometer on the surface of Mars. And this is exactly what we did. So the deployment of size, so this is the seismometer and the wind and thermal shield. And we have used the mechanic arm to place the seismometer on the surface firmly, and we also have put the WTS, the wind and thermal shield, on top of the seismometer. And there, it can sit there and listen to what is happening on the surface of Mars. So what can earthquakes or Marsquakes tell us? They tell us something about the source. If Mars is active, we should expect to hear a lot of Marsquakes. They also tell us about structure because seismic waves travel through the interior of the planet, and we get the shape and the amplitude change as they travel through the planet. If we're lucky, they also tell us something about the receiver locality. And on Earth, I just want to show this this website. I'm not sure. Can you see it? No. Probably not. Okay, so well, if you go to your USGS website, you can see what is all the big quakes that are happening on the Earth right now. So I just have a screenshot here where these red lines are the plate boundaries. So Earth has active plate tectonics where the oceanic crust is subducting underneath the continental crust. And so places like the plate boundary are where we see a lot of earthquakes happening and a lot of volcanic activities. And I also looked at when is the last earthquake for Denmark. So there's one like 3.5 or 3.6, 8 years ago or something like this. But it is very easy to understand because Denmark sits somewhere inside the plate. So earthquake on Earth, they tell us about the plate tectonic activities. We also used earthquake to understand the interior of Earth. So for example, the identification of an outer liquid core is using S waves because P waves and S waves are two types of waves that generated from an earthquake, and S waves do not travel through liquids. So so the liquid core creates this S wave shadow zone, which from that we can infer the size and the existence of a liquid outer core. And speaking of the inner core, we have to mention a Danish geophysicist. And this is one of the reasons that I was really motivated to give this talk, because last time when I was walking downtown Copenhagen and I ran into this memorial where you can see there's a sphere of Earth with sketch of different seismic waves traveling through it. There is a seismograph and there's a little sketch of Inge Lehmann. So she's a legendary Danish geophysicist, and she has discovered the inner core. So she was studying this earthquake in 1929, and she realized if you have an inner core, you can explain some of the reflection of P waves at the inner core and outer core boundary. And this is just given a very small amount of data, and she came up with this inner core, outer core, and mantle simple model of Earth's interior. And after 30 years of constant observation, people have finally confirmed that this is actually what is happening inside the Earth. So it's quite amazing. She lived a very long life for 104 years. and she has done a lot of work on seismology, and she discovered this discontinuity in the mantle and did a lot of work on the surface waves as well. Yes, so she was, so that was the reason we discovered the inner core first. And I just want to give an overview of what earthquakes can tell us. And now we go back to Mars. So what have we found so far with insights with the seismometer? So this is a graph of seismic activities on Mars. On the y-axis, you have different days. So from the 80th day on Mars to the 29th. On the x-axis, you have the time of the day. So from 0 o'clock, 1 o'clock, 7 o'clock to the morning, to the afternoon, to the night. And you can see that the color here in the graph represents the noise, or it represents seismic activities. So either way, it will show up as brighter color. And you can see there's a huge area from early morning to late afternoon where you have a lot of noise, and this is because of the weather cycle on Mars. But luckily, we have this quiet period at night that we can start to detect a lot of the seismic activities. And different symbols here represent seismic events, and they represent different type and different quality, the colors. So up to now, we have already detected more than 500 Mars quakes, and the number is changing with time. So here I'm showing two of the largest events on Mars, and that compared to similar events on Earth at similar distances. So the largest one we have is still like 3.6 magnitude. This is not exactly the same on Earth because we have some scaling transfer, but you can take it as a measurement similar to what we have on Earth. On Earth, you need a magnitude 5 or 6 to destroy houses. At magnitude 3.6, you can hardly feel anything, I think. But you see the seismic waves have similar patterns as the seismic waves on the Earth. We have the P wave and S wave arrivals, and you can also see that in the Mars seismographs. One thing that you have to notice is that the amplitude is hugely different. We have, this is 10 to the minus 9 meters, and on Earth, this is 10 to the minus 5. So on Mars, it is much, much harder to detect a Mars quake than earthquake. This is a graph showing how active Mars is compared to the Earth. We have the seismic moment on the x-axis and the cumulative number of events. So because we have fewer larger quakes than smaller quakes, so you have these lines on these parallel lines on the graph, and moonquakes are here. So there are fewer moonquakes because Moon is less active, and we have Earth global is up here. So Earth is much, we have much more seismic activities. And this is what we observed for Mars. This is kind of a bit lower than what we predicted, but if we remember, we have this huge period in the morning that we cannot observe anything. So we kind of expect we would see more events. So if we scale this up a little bit, it is what we in the range we predicted, and we confirmed that Mars is more active than the Moon, but less active than the Earth, and is more or less similar to the intraplate activities on Earth. We also can have some ideas about where the largest Mars quakes come from, and up to now, we have these 3 larger quakes where we can start to pick up the PNS arrivals, and we can, with a lot of modeling, we can figure out where they are exactly on the surface of Mars. And we notice that these are all come from the same area near Cerberus foci. So this is an active volcanic area. So Elysium Bulge is one of the largest volcanoes on Mars. And here the forces are these fractures due to volcanic activity. And this is where we do expect a very recent volcanic activities. So it kind of fits the story that we think on Mars, there can still be some local activities and only in certain regions of Mars. But we still need to wait for more quakes to see if we can see the global pattern. So in the end, I just want to mention InSight is not the only mission that's tried to do solar system seismology. With the moon, we have a lot of Apollo missions that had humans instead of a robotic arm to place the seismometer on the surface of the moon. So we have a relatively good understanding of the moon. We have tried to do this with Venus. So Verena 13 and 14 are Soviet Union space probes, but Venus surface is very hard to land. It is high pressure and high temperature, and these probes just died in a few hours after landing, so we didn't have any data from there. And we don't really we never have tried for Mercury. And if we consider what we have learned about Mars and Moon and compare to Earth, we really realize how extraordinary our Earth is. We have the liquid outer core that generates the magnetic field that protects our surfaces from solar radiation and high energy particles. We also have hot and convecting mantle. We have the plate tectonic features where the surface, the crust can be recycled into the mantle, and how that has affected the weathering cycle and the climate evolution, we don't really know. And we are also the only planet with a really water-rich surface. I mean, Mars and Venus may have had water before, but right now it is a dry world. So how does Earth go from these hot balls of dust, just like the other planets, to the Earth we have right now? It's really still a mystery, and the planetary scientists are trying to understand by looking at the interior of these planets. So I hope we will have more space missions to go visit these planets, and maybe we'll have more answers by then. Yeah. Sorry, I didn't look at the time. I don't know if it's okay.
I think everything is all right. Okay, so thank you very much, Lou. And now we have some time for questions, which you can put in the YouTube chat. And I see that we already have 3 questions, but you can continue putting your questions there, and we will try to make sure that Lou can answer them. Okay, and so the first question is from actually our co-host, Rajika. So you said that Mars would have a wobble in its rotation if it had a liquid core, and Earth has a precession. So is the Earth's precession related to the liquid core? And for those who don't know, precession is the change in time of the Earth axis of rotations tilt. So this axis can do this, and this is precession. So do you know if it's related to us having liquid core?
I didn't get the first half of the question. Second half about
yeah. You mentioned that Mars can have wobble in its rotation if it had liquid core.
Yeah.
So on Earth is precession is Earth precession this wobble that we have because of liquid core, or is it not related?
Liquid core definitely has an effect on the rotation of Earth, but on Earth we also have ocean and tide and we also have a very large moon. So all of these affect the motion of Earth, and so there's geodesy, there's whole discipline to study how Earth moves, and that's the extent I can answer. I think Earth's precession is affected by a lot of things, but liquid core definitely plays a role.
Yeah, thank you. And we have a next question, which is from Jorgen Skud. How sensitive is the InSight seismometer And would it be able to detect a part of a spacecraft crashing on the opposite side of Mars?
That's a very good question. So how sensitive it is, I cannot really describe by numbers. I know that when we send the seismometer, we say that if there is a butterfly that lands on the seismometer, we would be able to detect it. And as of the other question about whether it can detect the crash of another spacecraft, this is something that we are actually trying to do on the team. There is a team that look at impact, and they actually calculated if we can observe the Perseverance landing. So Mars 2020 is the mission that just went to Mars, and they placed a rover on the surface of Mars. So as it lands, we are supposed to hear something from the seismometer, but I think we didn't really see it happening, but we do have, we did a lot of modeling about whether we can hear, we definitely cannot hear the landing because it is too far away, but we might be able to hear some of the atmospheric signal. But in addition to that, we know there is another landing that's going to happen in a few months. I think it's in May or in June, that the Chinese Mars mission called Tianwen-1 is also going to have a rover that's landing on the surface of Mars. And I think the planned landing site, they had two large areas, but one of them is in Utopia Planitia, which is very close. It's not very, very close, but it's closer to Mars 2020, so that we do expect we can see more of a signal from that landing. And this is why I think they were trying to have communications with the Chinese side to know exactly when it happens, because it is very important to have a high sampling rates operation at that time to obtain the signal, to compare if we can see that happening. But it is a very good question. It's something that we do try to do. And if, in addition to that, we also try to observe meteoroid impacts. So if we see a meteoroid impact on the surface and we know where it is, it really helps us to calibrate this. And in the course of the mission, we have observed impacts using images. So we keep checking these images on the surface of Mars and see if there are new impacts coming up. We have seen some new impacts actually quite close to the landing site of InSight, but they are too small to be detected. So we are going to keep looking for that, I guess.
Thank you. That's actually, yeah, that's amazing to know now. And next question, again from Rajika, which I guess is very much related to what you were discussing now. So, what causes Moon and Mars quakes if they don't have tectonic plates? I mean, you already discussed about that they can have quakes when stuff falls on them, but do they have anything internally produced?
Yeah. We think there are a few different ways to have Mars quakes and moonquakes. One of the typical way, because on Earth you have, like, earthquakes typically happen if you have tension built up in the rocks and it suddenly breaks, right? On Mars and Moon, we don't have plate tectonics, we don't have plates like crashing into each other, but we do have a hot interior that is cooling through time. So if you have hot rocks that are cooled through time, and it might create tension within the rock, and at some point it breaks and creates these activities. So these are typical intraplate seismic events. We also have them on Earth, and this is one of the main sources that we would expect from Mars and from the Moon. But we would also expect seismic activities from volcanoes. Volcanic activities, they have their typical type of seismic activity, and we expect to see some meteoric impacts. Impacts are usually smaller quakes, so because you need to couple the energy to the surface to create a larger quake, and that is one possibility. And if we have a larger impact, we would be able to see it. I think there is also another type of quake that we think might be happening is with the tides, because Mars has two moons, Phobos and Deimos, and the interaction between the Moon and Mars may create some tidal forces that create seismic activities. But those should be much harder to detect. Yeah, so going in, we expected a lot of quakes happening, but yeah, I think we only see like relatively smaller quakes until now, but we hope we might see bigger ones, which would be cool.
Okay, thank you. And we need to keep in mind that we are a bit over time, so we have also three more questions, and let's now be the last moment where you can put more questions. But after that, we will need to proceed later. Yeah. So next question we have is from Jorgen. How can you determine the direction and location of seismic activity with only one seismometer? Actually, I'm also curious now. How?
Yeah, that's another very good question. I mean, like, you're an expert of insights. It is very difficult, and the ideal way to do seismology is to have multiple seismometer on the surface, and then you can use triangulation to figure out where the seismic event come from. So with one seismometer, it is really hard. But this is what we have. It's a discovery mission. We only had one chance to put one seismometer on the surface, and that's what we did. And apparently, the seismologists figure out very smart ways to do this. First is to look at the P and S wave. So using the travel time, they can kind of back out the distance. With a lot of assumptions about the seismic velocity in the subsurface. So if we know the seismic velocities and we know the travel time, we can kind of calculate the distances. But you can only do that if you have clear PNS arrivals, and that is the case for the three larger quakes we have. And then we need to know the azimuth angle. And for size, the VVB seismometer, it has three components. So it can detect motion from X, Y, and Z directions. So using these different components in the horizontal plane, you can kind of back out what is the azimuth. So this is why that you end up with some uncertainties in the azimuth and some uncertainties in the directions, but you can kind of understand where it comes from. And if it is a big signal, it helps us because the signal to noise is much better. And that is what we can do right now with just one seismometer. I think it's already amazing that's how much we can tell. But if we have a second seismometer, for example, it will be much better.
Yeah. So yeah, we have two questions left, and I think it's okay. So questions is from Lisa. What do we? Yeah. So the question is another planet. What do we actually expect in terms of the size, liquidity, solidity? Okay, I will read as it written. It's written in better English, I guess. Liquid solid nature of Venus. Yeah. What do we expect in terms of size and liquid solid nature of the core of the Venus?
I think, okay.
Do we have any expectations?
We don't have we don't observe a global magnetic field for Venus, which is kind of strange because Venus is a similar size of Earth and we don't know what happened. So I think we don't really expect to have a convecting core, but whether it has a liquid core, I don't know enough to say anything about that.
Okay, so we literally don't know, and we don't have. Yeah, that's how science is. Okay, and the last question is from the awesome Quantum. Do stars have these layers? If so, what are they made of?
So I know there are people who do seismology with stars and try to understand the interior of star structure, but I don't know what causes them and what are the different components. So maybe someone else has a better answer. Hannah?
Do you want me to?
Yeah, maybe.
Okay, I'm not an expert in this, but you're talking about like the sort of like astro seismology.
Yeah.
Yeah. So basically what's happening is that stars are basically a balance of gravity and that would be sort of pulling the star together, and then outward pressure that is keeping the star from collapsing. And that outward pressure actually creates these standing pressure waves. And there's a whole bunch of different modes that those waves come in. And so you can for some stars, I think ones that you can are very bright, you can actually measure those modes. So I think it is kind of like seismology, and I think they're also called P waves. So, but it's not from tectonics or anything like that.
Yeah.
So it's even harder to study, I guess. Okay, I guess that means thank you. Thank you for your answers, and thank you, YouTube chat, for your questions. I guess now we have time for our break and combined with a quiz. And Rajika Kuravita, the one who you may know as a host of all the other events before this one, will take over to lead you through the quiz.
Yes. So, hello. Can people see me? Oh, wait, hold on. I guess I don't know how to view myself. Am I sharing a screen? No. Sorry. Because of the way that Zoom is working, I can't see myself. So I will put myself over here. Speaker gallery. So hi, people on Zoom. I am Reggie, as you might have seen from previous events. I am going to share the quiz link on the YouTube chat right now. So there we go. And the quiz is now open. So we will just give you time to do the quiz during the break. And the prize for the quizzes is free seats to the next live event, which we are very certain it's going to be live in May, which we're going to be talking about galaxies far, far away in the Big Bang. So that'll be fun, and also some free drinks. So yeah, have fun with the quiz and have a nice break. And I guess we'll resume at 8 o'clock. Also, if you've been enjoying Astronomy on Tap and you like the content that we bring you, please consider donating to us so we can get gifts for our speakers eventually, prize money to pay for our prizes, and also produce merch. Yeah, thanks. So I guess I will stop this and... Oopsie daisy.
Oh, sorry, muted.
Yeah. So, hello, welcome back, everybody. And I guess we will announce the winner of the quiz after the next lecture. And now, Hannah will take over and will tell us more about exoplanet atmospheres. And I hope we will see, or maybe not. I don't know. I actually don't know the content of your lecture, but I hope we will see what makes Earth so special by the means of comparing it to all the other numerous planets we have out there. And Hannah, when you're ready, you can start.
Okay, I'm going to assume you can hear me. So I'm going to share my screen. Okay, if you can't see this, someone tell me. Yeah, thanks so much. My name is Hannah Diamond-Lowe, and I study exoplanets and their atmospheres. So this talk is going to also be kind of an overview of the state of the field of exoplanets and where we're at and trying to detect life on those other exoplanets. So this talk is called Out of This World, Searching for Life on Exoplanets. And I always like starting with a picture of Earth, which this is. This is a picture of Earth and its atmosphere from the International Space Station. And I want you just to appreciate all these amazing features our atmosphere has. It has cloud cover, patchy cloud cover. It also has these various layers in the atmosphere. Actually, let me get my laser pointer out here. Okay, but so we went to Mars in Lou's talk, which was really great. And now we're going to go even farther. So out beyond our own Earth, beyond the solar system, and to stars or to planets around other stars. So just to make sure we're all on the same page, what exactly is an exoplanet? It's very simple. An exoplanet is a planet just like Earth or Mars or Jupiter, but it orbits a star other than the sun. So if you, next time it's a clear night, maybe tonight, and you go outside and you see stars out, you can think to yourself that actually what we know now is that almost every star has a planet around it, at least one. So actually, planets far outnumber stars in the galaxy. So there's a lot of space, no pun intended, to explore. And how actually are we finding these planets? So there's a bunch of methods, but I'm going to focus on the two most common ones and the two that have delivered us the most exoplanet detections. And that is exoplanet transits and radial velocities. And we actually get some very important measurements from each of these methods that is going to help us understand what these planets are like and where we can start looking for extraterrestrial life. So the transit method is pretty simple. You have a star and you monitor the brightness of the star over time. And if there is a planet orbiting this star, and if the orientation of that planet's orbit is such that it passes in front of the star from our point of view, you will eventually see this dip, this decrease in the star's light. Once the planet passes by, the brightness will go back up to the previous level. And you need to see multiple of these transit events. If you just see one, it might have been a planet, but we're not sure. But what's so great about planets is they keep coming back around in their orbits. So if you see multiple events that look like this at some periodic interval, you can be pretty sure, okay, there's a planet there. And we get quite a few different measurements from observing a planet transit, but the important one to remember is that from this we get the planet's radius. We get to know how big it is. And the next method, very popular, is the radial velocity or the wobble method. This one is a little bit more complicated, but basically what's happening is you have a planet and it is in the orbit of its host star. So it is gravitationally bound to that host star. That's how the planet stays in orbit. That's how Earth and all the planets in the solar system stay in orbit around the sun. But gravity is a two-way street. So actually the planet is also introducing a little bit of a gravitational pull on the star itself. So this is a very exaggerated schematic of this, but basically the star is also wobbling around the common center of mass. And as the star moves towards the Earth, light from that star is blue shifted. And as the star moves away from the Earth, that light is red shifted. And it's by that shift in blue shift and red shift, again, periodically, because the planet is going around and around, that can tell you that there is a planet there. Importantly, from this measurement, we get the planet's mass. Now, a thing about the radial velocity method is the planet does not necessarily have to transit. The wobble, this gravitational wobble, is induced even if the planet is slightly misaligned from our point of view. But if you flip that around and say, well, if there's a transiting planet, if that whole system is close enough, we can also do the radial velocity method. And then you would get both the planet's size, the radius and the mass. Okay, so these are the main methods. And I want to give you a sort of picture of just what kind of planets we've found so far. So this is a plot showing basically all the detected planets we have, with the mass of the planets on the y-axis as a function of the orbital separation. So how far the planet is from its host star. This is in astronomical units, where 1 AU is the distance from the Earth to the sun. So here's Earth sitting at 1 AU. So I've put on here some of the most common ways of detecting planets. And as you can see, the radial velocity and the transit method win by far. There's lots of blue and orange points on this figure. Another thing you might notice is that if we look at the solar system planets, so Earth, Venus, Mercury and Mars are too small to be on this figure, sorry to them. But Jupiter, Saturn, Neptune, Uranus, all of these solar system planets kind of reside in an area of this figure where there aren't any exoplanets. That is not because exoplanets don't exist far away from their stars. It's because the farther away a planet is from its host star, the more difficult it is to detect. And you can just think about the geometry of the planet transit. If you're looking for a planet going around a star, if that planet is farther away, even a slight misalignment of the orbital plane will mean that we don't actually see that sign, that telltale dip of the planet passing in front of its star. Similarly, with the radial velocity method, if the planet is farther away from its host star, that gravitational influence that the planet has on the star is a lot smaller. So you're just not going to be able to see that wobble. But we can also look at this the other way and say that, well, we found a ton of exoplanets where we don't seem to have planets in our own solar system. And that's actually really exciting. The field of exoplanets is only about 25 or 30 years old. But we have found so many types of planets for which there is really no analog. There's really no planet like it in our own solar system. So one I want to point out is these hot Jupiters. These are Jupiter-like planets, but they orbit closer to their host stars than Mercury does to the sun. These were very unexpected. They're actually pretty rare, but they're very easy to find because they're really close to their stars. They're big. They induce a large gravitational wobble, so they're a little bit overrepresented. If we move down in mass, we have another surprise. These are planets known as sub-Neptunes. We don't have anything like this in our own solar system. We think these are kind of like Earth-like planets, sort of a rocky core, but they have to be surrounded by a thick hydrogen and helium envelope, more kind of like a Jupiter. So we've sort of named these sub-Neptunes. It's not a great name because Neptune, you see, is far out here. Neptune has a lot of ices. These planets are fairly hot. We don't think they have a lot of ices. Maybe they have some. But these were also a surprise, especially because we've actually found a lot of them. And if we get even farther down, we have these rocky terrestrial planets. And if we're going to look for life on other planets, we kind of need to start by looking in the mirror. We know what life, we only have one example of life, and that's us on Earth so far. And so if we want to look for that around other stars, we want to start by looking at the most Earth-like things we can. So these are kind of going to be the focus of the talk for the rest of the time. So how do we detect a rocky planet? Well, the same way we detect the planets I've talked about so far. But if you want to find small planets, it really helps if you look around small stars. And this is a pretty simple reasoning right here. If you have a solar-sized star, so a star like the sun, and you put a small terrestrial planet around it, you will see this transit dip, but it will be fairly shallow. Whereas if you put the same planet at the same relative orbital distance around a much smaller star, suddenly that signal really increases and you can actually detect it much more easily. And these smaller stars are called M dwarfs. There's actually another reason it really helps us to look around M dwarfs, and that's because they're smaller and also cooler stars. So here, for example, is a sun-like star, and this green ring around it is indicating the habitable zone. And so that is the area around a star where we think liquid water could be supported on the surface of a terrestrial planet. So you'll notice this sort of dotted line in the habitable zone around the sun is representing Earth. Planets closer in are too hot to support life, and this is true for, we don't see life on Venus or Mercury. Planets farther out are too cold. If you go to a much larger star, it becomes even more difficult because that habitable zone moves even farther out, and as I mentioned earlier, for planets farther out, these are just more difficult to detect, especially for the transit and radial velocity methods. But for smaller stars that are also cooler, that habitable zone becomes much closer in. And suddenly this is an area of parameter space that we can start actually detecting terrestrial planets. Okay, so what do we have so far? We've talked about getting radii and masses. So here we have planet radius and Earth radii and planet masses and Earth masses. And once you can measure both of these qualities for a planet, you start to be able to make some inferences. For instance, we can make these composition curves. So this would be, excuse me, a hydrogen and helium dominated composition. This is where the gas giant planets live. And down here we have a rocky composition. And right along this composition are the terrestrial planets of the solar system. So those are the big blue dots. This is Mercury, Mars, Venus, and Earth. And you can see that they have very similar bulk compositions. And we actually now have terrestrial exoplanets with masses, measured masses and radii that fall also on this curve. And that is really exciting because those bulk properties look very familiar to us. However, the big unknown here is, do these planets have atmospheres? And specifically, do they have atmospheres that support life? And we don't know. We don't know the answer to this question yet. And this is mostly because this composition curve doesn't tell us much about the planet's atmosphere. The atmosphere of Earth, while it is very different from the atmosphere of Mars or Venus, all of those are actually just very, very thin layers surrounding the planet. They do not add much mass to the planet, and they don't add much in terms of radius. So just measuring a radius and mass is not going to get you to a terrestrial planet atmosphere. So we have to be a little more clever about it. And that involves, well, there's a few ways to do this, but the most common now is to go back to the exoplanet transit and dig a little further down. So in this schematic, you have the star, you have the planet in its orbit, and you can see if you imagine an atmosphere around this planet, you're going to try to detect that in some fashion. And the way to do that is to think about the light from the star filtering through the planet's atmosphere on the way to our telescopes. So kind of shift this picture in your mind. And now we're over here. So here's star. This is the great alignment that we look for: star, planet, us. And these sort of concentric circles around this planet are representing the planet atmosphere. And, okay, so you have the planet radius and then the star's radius. And if we imagine that in this planet's atmosphere, it has some water in the gaseous state. We have water in our atmosphere. Sometimes it rains out, sometimes it's cloudy. And it is very reasonable that we would find water in the atmospheres of other planets. Now, the molecular spectral signature of water is very distinct, as it is for all molecular species. This is like a very specific fingerprint for each molecule. And we take advantage of that when doing transmission spectroscopy. So if we look across a spectrum, this is just showing the optical to infrared, but you can do this farther into the infrared and to some extent in the ultraviolet. If you look at, say, a wavelength around 550 nanometers where water is transparent, light from the star will pass directly through this planet's atmosphere, and we will measure this as the planet radius. However, if we also observe the planet transit somewhere, say, in the infrared, where water is very absorbing, suddenly the water is going to absorb that light from the star, and it is going to make the planet look bigger. And so we'll actually record a larger size for this planet. So this is kind of what that looks like. We can actually, you should recognize these as these planet transits. So here's light from the star, planet passes in front. And if you can observe this transit simultaneously at different wavelengths, you can measure the different sizes of the planet or how the planet size changes as a function of wavelength. And that will give you a clue about what's in the atmosphere. So here is some actual data of a terrestrial exoplanet orbiting a nearby small M-dwarf star. We have the planet, we have the transit depth, which is basically just saying how big the planet looks to us as a function of wavelength. So the data are these blue points with error bars. And I've compared this data to a model of what an atmosphere might look like. And if you think, well, that model doesn't match the data, you'd be right. Basically, this what we can do is rule out some atmospheric cases for these terrestrial exoplanet. But so far, we have not been able to detect the atmosphere on a terrestrial exoplanet. And that's okay. This is actually in line with what we think these atmospheres might look like, which are sort of tightly compacted to the planet's surface. We just need better telescopes and instruments. So looking towards that future, we have made huge strides recently, and we will make even more coming up shortly in terms of detecting and discovering the planets we need to be looking at, and then also making the next step in characterizing the atmospheres of those planets. So Kepler and TESS are two great discovery missions using transits. The HARPS spectrograph in Chile has done amazing work in terms of getting planet masses, detecting planets that way, and also measuring the masses for planets we've detected. This is just a sampling of some detection telescopes. There are definitely others. And similarly with characterization, we can do this both from the ground and from space. And I do want to highlight we're very much looking forward to the launch of the James Webb Space Telescope, which will be able probably to detect, well, definitely, if they're there, we'll be able to detect the atmosphere of a terrestrial exoplanet within the next 5 years. But to detect extraterrestrial life, especially via any kind of biosignatures that might be in the atmosphere, that's a bit more of an open question. That might be a couple decades ahead of now. And to go even farther out, because people sometimes ask me, well, you look for habitable planets, are we going to go there and are we going to live there? And the answer really is no. We have only searched a very small part of our galaxy. So this is our galaxy, the Milky Way. Here is the sun. And most of the planets, there are some exceptions, but most of the planets, the vast majority that we've detected, lie within about 300 light years. So that's not very far. If you look at the whole parameter space of the Milky Way, we have not searched a ton of it. And it is one thing to detect an exoplanet, it's another to try to get there. On the scale of space, it is not going to be a viable form of continuing humanity. We must do a better job of taking care of the Earth we already have. And so one final thought on this is that really there is no place like home in terms of the atmosphere that we have. So we have ozone in this atmosphere that protects us from UV sunlight from our star. So that's what gives you sunburns, but also it's very bad for cellular life. So if we didn't have this atmosphere, we would probably not exist as life forms as we do now. This is why we're so intent on finding atmospheres on other planets to determine their habitability. The atmosphere also keeps our surface temperature from changing too much. So even when we don't see the sun at night, we are still able to survive that night. And also the molecules in Earth's atmosphere are fine-tuned to support our biology, which is not a coincidence. That is actually, we evolved to be supported by this atmosphere. And that's it. Thank you.
Thank you. And I will remind to the chat that if you wish so, you can put questions in the chat and we will see them and we will react to them. And for now we already have some questions. And so the first one is, for a planet transiting a smaller star, would it be easier to miss a transit? Because it looks like the transit looks shorter around a smaller star.
That's a great question. I'm going to go back. Okay. Yeah, actually, it actually makes it, that's a really good point. So the transit is shorter when you look around a smaller star, but that actually makes it easier to detect. And that's because we detect these planets by monitoring a large sample of stars and looking for these dips. And so if it actually happens, if the transit is shorter, it's also happening more frequently. And so you're actually going to see more of them. And remember, it's seeing the multiple transits at periodic intervals that is revealing the presence of a planet. So that's a really good point. And we have designed our transit searches to actually make that an advantage for us.
Thank you. Yeah, while we're waiting for some questions in the chat, I also have some question. So you showed in the beginning, you showed the diagram with different exoplanets, like where you explained hot Jupiters and all the stuff. So, and you explained that on the right side, planets are far away, and that's why we just don't see them. But what happens on this weird circle between hot Jupiters and sub-Neptunes? Why there are no one planet in there? Like, why do, yeah.
Yeah, here. So this is a tough plot to show because it always looks like there's some real physical difference here between like, oh, there's lots of hot Jupiters, then nothing, and then we get to the sub-Neptunes. This is actually really mostly detection bias. So what it should look like is lots and lots of planets down here, and then fewer and fewer as you get to these larger planets. Although you may get some very large ones out here. That's sort of what's predicted. There should actually be basically no planets in this circle relative to the other ones, relative to the sub-Neptunes anyway. It's just that these are so easy to detect that it looks like we have a lot more of them, and it looks like there's actually this breakdown here. Yeah, does that answer your question? It's kind of unfair because it looks like there's something more going on, but yeah.
Thank you.
Yeah.
Also, we have another question in the chat. Has any spacecrafts tried to look at the atmosphere of Earth? Oh yeah. I was like, how do we know? How are we gonna know if aliens looked at Earth? But yeah, like I mean, we also have spacecraft. I guess spacecrafts that far away or not far away. Did we study Earth atmosphere this way?
Yeah, so that's been, I mean, we of course study Earth's atmosphere from the ground at Earth, and we also have a number of satellites orbiting Earth whose job it is to look at Earth's atmosphere. I'm going to put the end picture up again because it has such a nice look at Earth's atmosphere. Yeah, so for instance, the International Space Station is looking at Earth right now. This is the atmosphere. It's great. But since there have been missions to, as spacecrafts that are going farther out, farther away from the Earth, so leaving Earth's orbit, have actually turned around and looked at Earth from a distance. And these are sort of called like Earth as an exoplanet studies. Very famously, I believe it was with the Voyager missions, Carl Sagan famously suggested this. And so as Voyager left the inner solar system and moved away, it turned around and looked at Earth, and it's called the pale blue dot. It's just a very, very tiny luminous dot in the sky. I don't have a picture in this. I actually thought of putting that in this talk, and then I didn't think I'd have time. But if you look it up, it's called the pale blue dot, and it's kind of just an amazing image showing us that we just live on this tiny, tiny little planet just floating in space. And then, yes, subsequent missions have done a similar thing to prove the technique. Yeah.
Thank you. And we also have another question in the chat. How thick does the atmosphere needs to be? Does atmosphere need to be detected? Because some rocky planets have very thin atmospheres, and yeah.
Yeah, that's a really, really good question, and we're still kind of at the point where we haven't detected any atmospheres around terrestrial planets, but that's actually kind of expected. So if we think about terrestrial exoplanets, like we think about the exoplanets, we think about the terrestrial planets in our own solar system, Earth's atmosphere is much, much, much smaller than Jupiter's atmosphere. You think of Jupiter. Jupiter is just a huge ball of hydrogen and helium with like a kind of very dense little core in the middle. Whereas Earth is mostly, it's rocky, iron core, rocky mantle, as Lou was describing. And then we just have the thinnest of thin atmospheres around our planet. I think you're sort of alluding to what is maybe the difference between like detecting Earth's atmosphere versus detecting an atmosphere like Mars, which we just learned is a lot thinner than ours. And so, yeah, certainly Mars's atmosphere would be even more difficult to detect than Earth's. But all of them are more difficult to detect than these larger planets. So that's why we need these bigger telescopes and the more precise detectors in the near future. Yeah.
I see. Thank you. Yeah, and I think we don't have any more questions. So I guess that means that we going to have Reggie take over with the results of the quiz, right? Do we?
Yep. Yes, I can take over
Yeah.
with the
Thank
quiz
you.
results.
Thank you, Hannah, for answering all the questions. Thank you, chat, for questions. Yeah, and now the quiz.
Yes, so let me just go into gallery view. Yes, so we're back and we have a quiz winner, which was Awesome Quantum. So I will email you and ask you about when you want to come join us at the next event. So I'll quickly go through the quiz questions. So this isn't going to be the prettiest, but let's go through this. So the first question was, we expect houses will be damaged in an earthquake of more than what magnitude? And Lou told us that it was 5 magnitudes. That was the correct answer. Which of these images corresponds to insight? And as you might remember from Lou's talk, it was A. The next question is, HP3 takes Mars's temperature, revealing. Oh, sorry. Yes, can you hear me? Yeah, you can. HP3 takes Mars's temperature, revealing how much heat it is still flowing out of the interior of the planet. But what causes that heat? And that was radioactivity. That was the answer. And then which below was not one of the major contributions of Inga Lehman to the understanding of the interior of the Earth, and that was proving the liquid state of the outer core. And question 5 was, how many of the rocky planets, Mercury, Venus, Earth, or Mars, have a global magnetic field? And this was surprising to learn. It's actually 2. So Earth has a global magnetic field, and Mercury has a very weak global magnetic field. So that was pretty cool to learn. The Earth has a large moon compared to the other rocky planets. So how do we think the moon formed? And our best guess is that it was hit by a large object which threw its outer layers into space and later formed the moon. And question 7 is, what is the most abundant element in the Earth's atmosphere? So while we breathe oxygen, it's not actually the most abundant, and the most abundant is nitrogen. But when you compare that to Venus and Mars, so what is the most abundant element in their atmosphere? It's actually carbon dioxide. And then question 9 is, how big is the smallest known exoplanet around a living star? And apparently we've detected planets down to Mercury size, so that's pretty cool. And the final question is, approximately how big do we think a planet can get before its gravity gets so strong that it must hold onto a thick atmosphere? So kind of like those Neptunes that Hannah was talking about. And we think that it can get up to 10 Earth masses, and when it's 10 Earth masses, then it just wants to hold onto a really, really thick atmosphere. So that was the quiz. We hope that you enjoyed it, and yes, I'll contact the winner, and we'll see you next month for another quiz.
Yep, thank you very much. And with you were Reggie for the quiz, Lou for Mars, and Hannah for exoplanets, and me, Georgie, for hosting today. Thank you.
Bye.
Good night, everyone.